In this example, we study analysis of variance, known as ANOVA for short. Sometimes we want to compare means across many groups. Why not pairwise comparisons? If there were 3 groups, we might be tempted to compare the first mean with the second, then with the third, and then finally compare the second and third means for a total of 3 comparisons. Don't do this. If we have many groups and do many comparisons, it's likely that we will eventually find a difference just by chance, even if there is no difference in the populations. Instead, we should apply a holistic test to check whether there is evidence that at least one pair groups are in fact different, and this is where the ANOVA saves the day. So with proportions, we saw the chi-square test for comparing many different proportions. ANOVA works similarly to compare many different population means. ANOVA uses a single hypothesis test to check whether the means across many groups are equal. So our null hypothesis says the mean outcome is the same across all groups if we want to write it with words. Or if you prefer to write the null hypothesis in statistical notation, you could say the null hypothesis is that mean 1 equals mean 2 equals ... for however many means we have, all the way up to the last mean, which we denote mu k. And then mu I, where I is standing for whatever index we're at, 1, 2, etc., represents the mean of the outcome for observations in category I. So we use this number I in statistics to stand for the index when we're going through numbers for ordering different groups or counting different groups. The alternative hypothesis is similar to the alternative hypothesis for chi-square testing, except now we're looking at means and not proportions. So the alternative hypothesis says at least one mean is different. So let's investigate. So our research question that I came up with is to investigate, is batting performance related to player position in Major League Baseball, or MLB for short? So over on the right-hand side, we've got a picture of my favorite baseball team, the Oakland A's, playing at the Coliseum. That's our local East Bay baseball team. This is from last year. There's no games right now this year. So step 1 is to write research hypotheses. So the null hypothesis is going to say that the mean batting averages, which is calculated as the hits divided by the at-bats, if you're into baseball statistics, is equal for all field positions. Or in statistical notation, you could say, does the null hypothesis is where mu for the outfielders, that's what the OF stands for, is the same, so the mean is equal for the infielders, that's the IF, is equal to the mean for the designated hitters, that's the DH, is equal to the mean for the catchers. So the OF, IF, DH, and C stand for our different field positions: outfield, infield, designated hitters, and catchers. These are the ways that the players are classified. And then the alternative hypothesis would say that the batting average, which we say mu with whatever index we're using, varies across some or all groups. So if at least one group is different, then we would go with the alternative hypothesis. So step 2 is we're going to go find the data. So we're going to go to StatCrunch and go to data sets and do some exploring and find the data file MLB 2019 hitting. And we are going to see how the data looks. It's sorted by the at-bats, and you could find your favorite player. My favorite player is in row 2. And then for a challenge, you can see if you can define all the column acronyms. So here in StatCrunch, we'll go down to data sets. And we'll go type in MLB hitting here and see if our data file comes up. And you can see I've got some older years in here, but we're going to look at the 2019 hitting. So I said my player is number 2. It's sorted by the at-bats. So we can see Whit Merrifield from Kansas City had the most at-bats. And then my favorite player, Marcus Semien from the Oakland Athletics, had the second most at-bats in 2019. So that meant he was at the plate a lot. He's a local guy. He grew up in El Cerrito and played Little League there. And then he went to college at Cal and he went to high school in Berkeley. So that's one of the reasons he's my favorite player. So you can scroll down and find your players. So our columns have the player name and the teams. Those are categorical. Positions are also categorical. And then the positions have been grouped by the field position, so we can compare infielders and outfielders with catchers, and then the players who just bat are called designated hitters, so they're noted with a DH. And then we've got G, which is the games that they played in. So it looks like these first two players played in all of the games all season. R is the runs, H is the hit. 2B is if they got a double, 3B is if they got a triple, so those are less common. And then you can scroll over and see home runs, runs batted in, and I'll let you investigate these other common baseball statistics. You can Google them if they are not known to you and have some fun looking that data up. All right, so now we're going to do some box plots for the batting average. So we are going to select graph box plot, and then we're going to group by the field positions. And we're going to investigate if we visually detect a significant difference, is the variability approximately constant, and are there any outliers of concern? So we'll go to graph box plot. So we're going to do box plots for the batting averages. That's AVG. And then we are going to group by the different field positions. And you can draw your boxes vertically or horizontally. We'll use fences to see if there's a lot of outliers or not. So not too many outliers. There are some lower outliers. These might be players who just didn't play. That's why they've got zeros here, but they're still listed. Overall, the central boxes seem pretty consistent. This is real data, so they're not going to be exact matches. And most of the box plots look approximately symmetric. We see some skew in the designated hitters there, but things are roughly consistent. So for question 1, can you visually detect a significant difference? Well, the medians are pretty close, so visually we can't say that there's a big difference. Is the variability approximately constant? With a rough definition of approximate, we'll say sure. The central boxes are pretty close in size. They differ from about 0.25 to 0.30 batting average. And then there were some outliers, but they weren't necessarily of concern. So these are the conditions that we check to make sure we can use analysis of variance. If we had some really different looking box plots or some outliers that were way far out there, then we might be concerned and say maybe we don't want to use this method of analysis. But since we have close enough to nearly constant variance, we're going to say that we can use this analysis of variance approach. All right, so now we're going to go look at the summary stats. So we are going to go summary stats, columns, and then we're going to figure the batting average is what we want the statistics of, and we're going to group by the field position. And then we're going to look at the sample size, the mean, and the standard deviation. So let's head back to StatCrunch and do that. So we will go to summary stats, columns. So we want the batting average, that's AVG. And then we want to group by the field position. And we just want the sample size, the mean, and the standard deviation. So I'm just going to use the Control or Command key to highlight just those statistics. And here's my results. So we see there's a lot less designated hitters. If you wanted to make an argument and take those players out, you could. The results don't change too much. The means are all pretty close. They range from about 0.19 or 0.198, which is around to 0.20, up to about 0.23. And the standard deviations are all around 0.07 or 0.08, so close. So I recorded my values here. I recreated the table. And then we want to say, well, how do the means and standard deviations compare? Close or far apart? So for the most part, the means are close, all around 0.20 to 0.23. And the standard deviations are close, all around 0.07 to 0.08. What we're looking to make sure is that there's not one group that's way far off of the other groups. So for the most part, our values are close here. And then we want to go to graph histogram and make histograms of the batting average for each field position. And we're going to check to see, are the observations independent within across groups? Is the data within each group nearly normal? And is the variability across the groups about equal? So we are going to assume that there's not a dependence between position and the batting average, that players aren't selected for a given position because of how they bat. So we're going to assume things are independent. We know there's no overlap in the data set because each player is only assigned to one field position. So let's go check to see if the data is nearly normal and if the variability is about equal. So we're going to head down to select the column for the batting average. We're going to group by the field position and hit compute. All right, so here's the catchers. We can really roughly say this is normal. It's got a left skew there. But with a real rough, it's close-ish to normal. It's got one peak. And then the spread on each side is it's skewed, but it's about equal from the center. Here's the designated hitters. This is, again, it's kind of about the same distance from min to max with the center there. It's definitely got a left tailish here, maybe. It looks like there's less values in the left. So again, we're being really, really rough here when we say, normal-ish. And then here's the infield. Again, we've got this left skew, but the center is about the middle. And the values go from 0 up to a little above 0.5. And then outfield, again, really roughly normal. We're going to say it's close enough for us to use the analysis of variance. If we saw something really, really skewed or something with 2 peaks, then we'd say, this might not be okay to use this data. Again, with real data, it's not going to be perfectly normal. And the variability, they all seem to range from about 0 to 0.5. So we will say that these conditions are met, and we can go ahead and use the ANOVA test. So the ANOVA test gives us something called the F statistic. In the past, we've seen the Z statistic and the T statistic. So the ANOVA statistic has this letter F, named after the statistician Fisher. So we need a way to judge the variation in the sample means to determine if the differences are statistically significant. So if we find that the sample means are not close together, or at least one deviates substantially from the others, we'll say that we have evidence against the null hypothesis and that the population means are not equal. Otherwise, if the sample means are close together, we'll say that we do not have evidence against the null hypothesis. That is, the difference in the sample means are not statistically significant, and the sample means could come from populations with equal means. So the F statistic measures the variation in sample means relative to the variation in the data within each sample. The F statistic is a very complicated, and we will not compute it by hand, but in essence, it's a ratio of variations, hence why it's named the analysis of variance. So it's a calculation of the variation in those sample means and the variation in each sample. And if you take an advanced statistics class, you can see the formula. For our class purposes, we are very happy that StatCrunch will do this calculation for us. So we are going to go into Stat ANOVA one way, and we're going to choose responses in the average for the batting average column, and the factors are going to be the field positions. So we go to Stat ANOVA one way, because we're just working with one variable here. Choose the second choice, values in a single column. And we choose the average, and we're going to let our factors be what field position the players are in. And here's our results. So the summary statistics are the same that we calculated earlier, plus they've added the standard error. And then down here we have our F statistic, which is about 8, and our p-value, which is very small. And so we will see our results. So you can see they have factored in field position as degrees of freedom 3 because there was 4 categories. All right, so the F statistic and p-value are recorded, and then we write our conclusion. So since the p-value is very small, we reject the null hypothesis. There is evidence to conclude that the batting average varies across some field positions. So the ANOVA test is something that you'll use when doing research in other fields besides math class very often when you're looking at different means across many groups. And it comes up a lot in medical research or in engineering research or sometimes even in social science or demographics research.